K2-18b breakthrough, scientists uncover evidence of possible life on an exoplanet 124 light-years away. Introduction. On April 17, 2025, a groundbreaking announcement from the scientific community ignited excitement and speculation regarding extraterrestrial life. Researchers utilizing the James Webb Space Telescope JWST reported compelling evidence suggesting the existence of life on the exoplanet K2-18b located approximately 124 light-years from Earth. The study centered around the detection of two sulfur-bearing gases, dimethyl sulfide DMS and dimethyl disulfide DMDS, which are predominantly produced by biological processes on Earth. Discovery significance. The significance of this discovery cannot be overstated. The detection of DMS and DMDS represents the strongest evidence yet for potential life beyond Earth, marking a significant milestone in astrobiology. The findings reached a 3 sigma statistical significance level, indicating there is a 0.3% probability that the signals could be attributed to random noise. However, the scientific community typically requires a 5 sigma threshold for definitive claims of discovery, which emphasizes the need for further observations. Characteristics of K2-18b. K2-18b is classified as a Hycean world, a term referring to ocean-covered planets characterized by hydrogen-rich atmospheres. This exoplanet is about 8.6 times the mass of Earth and 2.6 times its diameter, and it orbits within the habitable zone of its parent red dwarf star, where conditions may allow for the presence of liquid water. K2-18b completes an orbit in just 33 days, placing it in a unique position to maintain a potentially life-supporting environment. Research methodology. The observations of K2-18b involved monitoring its transit across its star, allowing the JWST to analyze how starlight filters through the planet's atmosphere. Different instruments were employed to gather independent data, reinforcing the findings related to the sulfur compounds. The latest observations utilized the mid-infrared instrument MIRI of JWST, which detected DMS and DMDS at concentrations exceeding 10 parts per million, significantly higher than the levels observed on Earth. Skepticism and caution. Despite the promising findings, scientists have urged caution. Experts have warned that the detected gases might also arise from non-biological processes such as exotic chemistry or geological activity. This highlights the necessity for additional observations to confirm the origins of these molecules. Professor Niku Madhusudhan from Cambridge University, who led the research, emphasized the importance of remaining skeptical and conducting rigorous testing to validate the results. Timeline of events. 2015, K2-18b is discovered, noted for its size and position within the habitable zone. 2023, initial observations by JWST detect methane and carbon dioxide, indicating the presence of carbon-based molecules. April 2025, researchers announced the detection of DMS and DMDS, marking a significant step toward confirming the possibility of life on this exoplanet. Differences among sources. Various sources highlighted different aspects of the discovery. One source focused extensively on the statistical significance of the findings and the implications for astrobiology, mentioning the need for future observations to reach the 5 sigma threshold. Another emphasized the skepticism within the scientific community, with some experts asserting that K2-18b's conditions may not support life as we know it. A third source provided vivid descriptions of the planet's environment and the potential for microbial life, while also cautioning against premature conclusions. Conclusion. The findings regarding K2-18b represent a pivotal moment in humanity's search for extraterrestrial life, blending optimism with the scientific rigor that necessitates further investigation. The implications of such discoveries could reshape our understanding of life and the universe, yet scientists are committed to a cautious approach, ensuring that any claims of life are substantiated through rigorous testing and observations. As research continues, the prospect of discovering life beyond Earth draws closer, posing profound questions about our place in the cosmos. The discovery of potential life on the exoplanet K2-18b, located 124 light-years from Earth, is a significant breakthrough in astrobiology. The findings, primarily based on data from the James Webb Space Telescope JWST, indicate the presence of two sulfur-bearing gases, dimethyl sulfide DMS and dimethyl disulfide DMDS, which are typically associated with biological processes on Earth, particularly those involving marine phytoplankton. However, several counterintuitive aspects arise from this discovery. 1. Statistical significance versus certainty. The detection of DMS and DMDS on K2-18b has reached a 3 sigma level of statistical significance, which means there is a 0.3% chance that the signals could be due to random noise. In scientific terms, a 5 sigma level requiring a probability of less than 0.00006% is considered the threshold for a definitive discovery. This suggests that while the findings are promising, they are not yet conclusive, highlighting the difference between intriguing hints and confirmed evidence of life. 2. Biological versus non-biological origins. While DMS and DMDS are known to be produced by biological organisms on Earth, their presence on K2-18b does not necessarily imply that life exists there. Experts caution that these gases could also arise from non-biological processes such as exotic chemical reactions or geological activity. This presents a paradox. The very signatures of life we seek might also be produced under conditions we do not yet fully understand. 3. Hycean worlds and life. K2-18b is classified as a Hycean world characterized by a hydrogen-rich atmosphere and potential oceans. The concept of Hycean planets challenges traditional views of habitability, as these environments may not resemble Earth's conditions. The idea that life could thrive in such radically different conditions raises questions about our understanding of life itself, suggesting that organisms might exist in forms and environments previously thought to be inhospitable. 4. Caution from the scientific community. Despite the excitement surrounding these findings, many scientists urge caution. The scientific process is built on skepticism, and the necessity for further observations to confirm these results illustrates the methodical nature of science. This contrasts with the public's tendency to leap to conclusions about the existence of extraterrestrial life based on intriguing data. 5. Implications of discovery. Professor Niku Madhusudhan, who led the research, suggested that this discovery could represent a tipping point in our understanding of life in the universe. However, this optimism is tempered by the reality that definitive proof is still a distance away. The notion that we might be on the brink of answering one of humanity's most profound questions presents a tantalizing but uncertain narrative. 6. Future observations and technological limitations. The research team estimates that just 16 to 24 additional hours of observation with the JWST could push their findings to the 5 sigma threshold necessary for a stronger scientific claim. This highlights the limitations of current technology in confirming groundbreaking discoveries, emphasizing that the quest for knowledge is ongoing and fraught with challenges. In summary, while the detection of DMS and DMDS on K2-18b presents an exciting possibility for the existence of life beyond Earth, it also reveals the complexities and uncertainties inherent in astrobiological research. These counterintuitive aspects underscore the need for continued investigation and caution in interpreting these groundbreaking findings. The recent findings regarding the exoplanet K2-18b, particularly the detection of dimethyl sulfide DMS and dimethyl disulfide DMDS, represent a potential breakthrough in the search for extraterrestrial life. While the excitement surrounding the discovery is palpable, there are several important aspects of the findings that are often overlooked but hold significant implications for the scientific community and our understanding of life beyond Earth. 1. Statistical significance and the 5 sigma threshold. The reported discoveries have reached a statistical significance of 3 sigma, meaning there is only a 0.3% chance that the detected signals are due to random noise. This is an important technical detail that many may gloss over. In the realm of scientific discovery, particularly in astrophysics and cosmology, a 5 sigma threshold 0.00006% chance of being a false positive is typically required for definitive claims. Thus, while the 3 sigma result is promising, it serves as a reminder of the caution that must be exercised before declaring the existence of extraterrestrial life based on these findings. The significance of this detail lies in the expectations it sets for future research. Achieving the 5 sigma threshold is essential for the findings to be widely accepted in the scientific community. This underscores the importance of continued observational efforts and highlights the ongoing nature of scientific inquiry, where each discovery necessitates further investigation rather than an immediate conclusion. 2. The environmental context of K2-18b. K2-18b is classified as a Hycean world characterized by its large size, 8.6 times the mass of Earth, and the presence of a hydrogen-rich atmosphere. While the detection of DMS and DMDS is exciting, the broader environmental context of K2-18b, its temperature, atmospheric composition, and potential oceanic conditions, is equally significant. Some researchers have pointed out that K2-18b's proximity to its red dwarf star could lead to extremely high surface temperatures, potentially making it inhospitable for life as we understand it. The debate over whether the planet's conditions could support life revolves around its classification as a Hycean world, which suggests that it may have vast oceans beneath a thick atmosphere. This complexity warrants attention, as it may influence the types of life that could exist there, or even whether life could exist at all. 3. Alternative explanations for the detected gases. While DMS and DMDS are associated with biological processes on Earth, their detection on K2-18b does not conclusively indicate the presence of life. There is ongoing skepticism within the scientific community about the potential for non-biological processes to produce these gases. For example, exotic chemistry or geological activity could generate similar signatures without any biological involvement. This skepticism is crucial because it emphasizes the need for rigorous scientific investigation. Researchers are encouraged to explore all possible explanations for the observed data, which could lead to alternative hypotheses about the planet's atmospheric chemistry. Understanding the full range of potential origins for these gases is vital in the quest to confirm or refute the possibility of life on K2-18b. 4. Implications for astrobiology and the search for life. The discoveries surrounding K2-18b have far-reaching implications for astrobiology. If confirmed, they could fundamentally alter our understanding of where and how life might exist in the universe. The notion that life could thrive in environments vastly different from those on Earth challenges the traditional criteria used to identify habitable exoplanets. This perspective shift is significant, as it opens up new avenues for exploration and research. It encourages scientists to consider a wider variety of planetary conditions as potential hosts for life, which could lead to the discovery of previously unconsidered exoplanets worth studying. The implications extend beyond K2-18b, potentially influencing future missions and research priorities in the search for extraterrestrial life. 5. The importance of interdisciplinary collaboration. The findings related to K2-18b highlight the necessity of collaboration across scientific disciplines. Astrobiology, atmospheric science, geology, and chemistry all play critical roles in interpreting the results and understanding the implications of the observed gases. By fostering interdisciplinary collaboration, researchers can approach the question of extraterrestrial life from multiple angles, integrating diverse perspectives and expertise to enhance the robustness of their findings. This collaborative approach is significant because it promotes a more holistic understanding of the complexities involved in identifying life beyond Earth. As scientists work together to unravel the mysteries of K2-18b, the synergy of different fields will be essential in developing comprehensive models and theories about the potential for life in the universe. Conclusion. The recent discoveries regarding K2-18b and the detection of DMS and DMDS have opened a new chapter in the search for extraterrestrial life. However, the nuances surrounding the statistical significance of the findings, the environmental context of the exoplanet, alternative explanations for the detected gases, the implications for astrobiology, and the need for interdisciplinary collaboration underscore the complexity of this research. As scientists continue to investigate these promising hints, it is crucial to maintain a balanced perspective, integrating excitement with scientific rigor to ensure that any claims about life beyond Earth are grounded in thorough investigation and verification. 1. Discovery significance. The detection of dimethyl sulfide DMS and dimethyl disulfide DMDS in the atmosphere of K2-18b has been heralded as the most compelling evidence of potential extraterrestrial life to date. This finding is significant because DMS and DMDS are known biosignatures on Earth primarily produced by marine phytoplankton. The fact that these gases were found at concentrations over 10 parts per million, thousands of times higher than observed on Earth, adds weight to the hypothesis that K2-18b could harbor life. However, the statistical significance of the detection currently stands at 3 sigma, indicating that while the evidence is strong, it is not yet definitive. Further observations are needed to reach the 5 sigma threshold required for a conclusive discovery. 2. K2-18b characteristics. K2-18b is classified as a Hycean world, characterized by a hydrogen-rich atmosphere and possibly vast oceans. It is approximately 8.6 times the mass of Earth and 2.6 times its diameter, placed within the habitable zone of its parent red dwarf star. The conditions on K2-18b, such as its size and location, suggest a potential for liquid water, which is critical for life as we know it. Its short orbital period of just 33 days implies a close proximity to its star, which raises questions about the planet's temperature and habitability. Some scientists have expressed skepticism regarding the planet's capacity to support life due to its high temperatures. 3. Research methodology. The observations of K2-18b were conducted using the James Webb Space Telescope JWST, employing various instruments to analyze the planet's atmosphere during its transit across its star. The latest findings utilized the mid-infrared instrument MIRI, which detected the sulfur-bearing gases at wavelengths previously unexplored. The independent nature of these observations, which confirmed earlier suspicions of DMS and DMDS, enhances the reliability of the data. The methodology underscores the importance of using diverse instruments and approaches in astrophysical research to validate findings in the quest for extraterrestrial life. 4. Skepticism and caution. Despite the excitement surrounding the discovery, the scientific community urges caution. Experts highlight that the detected gases could also arise from non-biological processes such as unique chemical reactions or geological activity on K2-18b. This skepticism emphasizes the necessity for further observations and rigorous testing to rule out alternative explanations for the presence of these biosignature gases. The commitment to scientific rigor is crucial, as premature conclusions could misguide future research and public perception regarding the existence of life beyond Earth. The ongoing debate about the planet's habitability reflects the complexities and uncertainties involved in astrobiological studies. 1. The discovery of the Martian meteorite ALH840001 1996. In 1996, scientists announced that a meteorite found in Antarctica named ALH840001 contained evidence that could suggest the existence of past life on Mars. The meteorite, believed to have originated from Mars, contained structures that resembled fossilized microorganisms. This announcement sparked a massive scientific debate regarding the potential for life on Mars and whether these structures were indeed biological or merely mineral formations. Subsequent investigations raised skepticism about the findings, emphasizing the need for rigorous verification of life indicators elsewhere in the universe. 2. The WOW Signal 1977. In 1977, Astronomer Jerry R. Emmon detected a strong narrowband radio signal while working on a SETI search for extraterrestrial intelligence project at Ohio State University. The signal, which lasted 72 seconds, was so unusual that he circled it on the computer printout and wrote "wow" next to it. The "wow" signal has never been explained or detected again, leading to speculation that it could be evidence of extraterrestrial communication. The mystery surrounding this signal continues to intrigue scientists and enthusiasts, highlighting the ongoing quest to find life beyond Earth. 3. The detection of phosphine in Venus's atmosphere. 2020. In September 2020, researchers announced the detection of phosphine gas in the atmosphere of Venus, a finding that stirred significant excitement in the scientific community. Phosphine is a gas that on Earth is primarily produced by anaerobic organisms. The discovery suggested the potential for microbial life in the sulfuric acid clouds of Venus. However, subsequent analyses and critiques raised questions about the data's reliability and the possibility of non-biological processes producing the gas. This case illustrates the complexities of interpreting biosignatures and the importance of verification in astrobiological research. Future outlook: predictions for K2-18b and the search for extraterrestrial life. The recent findings regarding K2-18b, particularly the detection of dimethyl sulfide DMS and dimethyl disulfide DMDS in its atmosphere, represent a watershed moment in the pursuit of extraterrestrial life. As scientists continue to analyze these promising signals, several future developments can be anticipated within the realms of astrobiology, planetary science, and technology. 1. Further observations and confirmations. The immediate future will likely see increased scrutiny of K2-18b's atmosphere through additional observations via the James Webb Space Telescope JWST and other advanced instruments. Researchers are aiming to achieve the 5 sigma statistical threshold needed for definitive confirmation of the biosignatures. This will involve dedicated follow-up observations, possibly within the next few years. As scientists refine their methodologies and instruments, we can expect more precise measurements that could either confirm or challenge the presence of life indicators on this exoplanet. 2. Advancements in astrobiology. The findings related to K2-18b could catalyze a broader renaissance in astrobiology, stimulating new research into the conditions necessary for life on other planets. This may lead to the identification of other Hycean worlds and similar exoplanets that might harbor life. The scientific community will likely explore exotic biochemistries and alternative forms of life that could exist under different environmental conditions, thereby expanding our understanding of what constitutes life. 3. Technological innovations. The quest for life beyond Earth is driving technological innovation at an unprecedented rate. Future telescopes such as the Habitable Worlds Telescope and the European Extremely Large Telescope are expected to enhance our ability to analyze exoplanet atmospheres in detail. These advancements will not only improve our capacity to detect biosignatures but will also contribute to the development of technologies that could enable direct exploration of these distant worlds, either through robotic missions or in a more distant future. Human missions. 4. Interdisciplinary collaborations. The research surrounding K2-18b will likely foster interdisciplinary collaborations among astronomers, chemists, geologists, and biologists. Understanding the atmospheric composition and potential habitability of exoplanets requires a multifaceted approach. This collaboration will enhance our methods of detecting life and interpreting the data we gather from exoplanets, leading to richer insights and innovative research methodologies. 5. Ethical considerations and societal implications. As we edge closer to potentially confirming life beyond Earth, ethical considerations will become paramount. Discussions about planetary protection, the implications of contact with extraterrestrial life, and the responsibilities of humanity in exploring and possibly altering these environments will gain prominence. The societal implications of confirming extraterrestrial life will also be substantial, influencing philosophy, religion, and our understanding of our place in the universe. 6. Caution and skepticism. Despite the excitement surrounding the discovery of DMS and DMDS, the scientific community will maintain a cautious stance. There will be ongoing debates regarding the origins of these gases, as non-biological processes could also account for their presence. Future research will focus on ruling out these alternatives, reinforcing the need for rigorous scientific validation before drawing definitive conclusions about life on K2-18b. 7. Public engagement and interest. As discoveries like those related to K2-18b capture the public's imagination, there will be a surge in interest in space exploration and astrobiology. This could lead to increased funding for research, more educational programs aimed at inspiring future generations of scientists, and a renaissance in space-themed media and popular culture. The prospect of finding life beyond Earth could unify humanity around a common goal, fostering a sense of shared destiny. 8. The broader search for life. The implications of finding biological signatures on K2-18b will likely extend beyond this single exoplanet. Researchers will redirect efforts to investigate other candidates within the habitable zones of nearby stars, using the methodologies developed during the K2-18b studies to explore a wider array of celestial bodies. This expanded search will include moons of gas giants such as Europa and Enceladus, which may also harbor conditions suitable for life. 9. Philosophical and existential questions. The confirmation of extraterrestrial life, even at the microbial level, will provoke profound philosophical questions about existence and humanity's role in the cosmos. Discussions around the implications of such a discovery will push humanity to reconsider its definitions of life, consciousness, and intelligence, ultimately reshaping our worldview. Conclusion. The discoveries surrounding K2-18b mark a potential turning point in the search for extraterrestrial life. As scientists pursue further validation of these findings and explore their implications, we can anticipate significant advancements in technology, a deeper understanding of life and the universe, and a shift in societal perspectives on our place within it. The journey ahead promises to be as thrilling as the discoveries themselves, inviting both excitement and caution as we tread into this uncharted territory.